So, let us continue from the last class where we were talking about the dual simplex algorithm, and we have solved one problem to check how the problem can be solved using the steps of dual simplex algorithm. We have also observed that how one vector will depart and how one vector will enter into the basis, which is just opposite to the normal LPP, where we were first we were checking which vector will enter and then we were deciding which vector will depart. So, please remember that for dual simplex method, first we have to decide which vector will depart and then we will check which vector will enter into the basis. Now, let us take another example of some other type. The problem is in the canonical form already. Maximize z equals 3 x 1 plus 2 x 2 subject to 2 less than equals type constants. So, in standard form, if you wish, you can write down maximize z equals 3 x 1 plus 2 x 2 subject to make both the less than equals type constants into equality constant by introducing slack variable. So, it will be 2 x 1 plus x 2 plus x 3 equals 5 and x 1 plus x 2 plus x 4 equals 3, where x 1, x 2, x 3 and x 4 is greater than equals 0. Here x 3 and x 4 are the slack variables. So, the basis will be x 3 plus x 3 equals 5 and x 4 equals 3, or in other sense the vectors in the basis will be x 3 and x 4 respectively. So, let us first formulate the initial table. So, here you are having x 3 and x 4. So, that here you are having a 3 and a 4. Of course, the coefficients of these slack variables are 0 in the objective function. So, you are writing 0 into x 3 plus 0 into x 4 in the objective function. So, it is 3 2 0 0, your values are 0 and 0. So, your b value is 5 and 3. So, 2 1 1 0 and you will get 1 1 0 and 1. Your z j minus c j is minus 3 minus 2. Actually, this is not required at all. This ratio will not work here. Minus 3 minus 2 0 0. So, what you are observing here? At first, what we should check? We should check the z j minus c j value. We have told that in the initial table z j minus c j should be greater than equals 0. But for this case, if you see z j minus c j is less than 0 for 2 for j equals 1 and for j equals 2. So, initially if you have remembered, we were talking about that in that case feasible solution may not be present. So, let us see how to obtain the solution, optimal solution, whenever in the initial table the optimality condition is not satisfied, that is z j minus c j is less than 0. Because the basic idea of dual simplex method is that you are always at each iteration z j minus c j must be greater than equals 0 and your feasibility condition may not be satisfied, that is for some problem your x b may be less than 0. But for this case it is the opposite one, that is z j minus c j is greater than equals less than 0 in this case. So, what I am doing first? I am writing z j minus c j is less than equals 0, less than equals 0 for all j. So, in general your conclusion is your solution is neither optimal nor feasible from here, your neither optimal nor feasible. Since it is not optimal, what I have to do? I have to create a new constraint by adding one artificial constraint. So, at what places you have how many variables? X 1, X 2, X 3 and X 4. Your Z j minus C j is less than 0 for which values? Only for X 1 plus X 2. So, if you remember, for the artificial constraint whatever we have written earlier, then I will create a new constraint where summation over x j should be less than equals 0 and m is very large. So, what is the value of j here? I have told your j will be 1 and 2, because for 1 and 2 only you have negative values for z j minus c j. So, therefore, your constraint will be x 1 plus x 2 less than equals capital M, where M is sufficiently large. M is sufficiently large. So, and of course, M is greater than 0. M is greater than 0 and sufficiently large. So, since this is a less than equals type constraint, so what I have to do? I have to introduce one slack variable and make it an equality constant. So, I can write it x 1 plus x 2 plus x m. This is equals m, where x m is your slack variable. So, please note this one, your x m is the slack variable in this case, and I am making this new inequality constraint into equality constraint by adding the slack variable. And how I have chosen value of j, that is j will be 1 or 2 or 3 or 4. It depends on how many, for how many variables z j minus c j is less than 0. Here I am finding for x 1 and x 2 they are less than 0. So, therefore, I have made first x 1 plus x 2 less than equals m, then x 1 plus x 2 plus x m, this is equals to m. Now, your next step was what? I have to find out for which j equals p, mod of z p minus c p has the maximum value, and for that variable will be replaced. So, I have to calculate now basically z j mod of z j minus c j. So, now and I have to take the maximum of that. So, maximum of z j minus c j, j is only 1 and 2, because you have taken only two variables x 1 and x 2. So, therefore, maximum of modulus of z 1 minus c 1 comma z 2 minus c 2. So, this equals max of your modulus we have taken. So, z 1 minus c 1 is 3 in absolute value. Similarly, z 2 minus c 2 is 2 in absolute value. So, that here it will be maximum of 3 comma 2 and this is equals 3. And what happens? This 3 is occurred for which one? X 1. So, effectively for which j equals p, z p minus c p is maximum? It is for j equals 1. So, for j equals 1, that is for the variable z 1 minus c 1 is maximum. So, therefore, which variable will be replaced? We have told now I will replace x p equals m minus x m plus summation j not equals p x j, means here p is 1. So, x 1 will be replaced by m minus x m plus j not equals p, means there will be only one variable then x 2, because j equals 1 and 2. So, your x 1 will be equals to m minus x m plus x 2. So, since j equals 1, this is happening. So, I have to replace x 1 will be substituted or replaced in both objective function as well as the constraint of the original problem. And what is the value of x 1? From that equation, m minus x m plus x 2. So, please note that this was your original problem. Now, from this original problem, your x 1 will be replaced by this value. Similarly, in the constants also x 1 will be replaced. So, 3 into x 1 into this. So, I am writing now the original problem again, maximize z equals 3 m minus x 2 will come. So, minus x 2 minus 3 x m. This simply if you substitute x 1 here, you will obtain this one. You will obtain this equation 3 m minus x 2 minus 3 x m. It was 3 x 1 subject to minus x 2 plus x 3 minus 2 x m equals 5 minus 2 m, x 4 minus x m equals to 3 minus m. This actually you got it from these two equations from the original problem, and you have added one more constant here. Please note that on the new constant the variable x 1 will not be replaced. It will not be replaced because ultimately you got it from here only. So, therefore, this is nothing but this one x 1 plus x 2 plus x m. So, that equation basically came from here itself. So, the third constant now we are adding as x 1 plus x 2 plus x m, this is equals to plus x m, this is equals m, where x 1, x 2 and x m all are greater than equals 0. Of course, your x 3 and x 4 are also there. So, in the basis now 3 variables will come x 3, x 4 and x m. So, I hope the method is very clear to you now. Whenever I have one z j minus c j less than equals 0, the optimal condition cannot be achieved. Since optimality has not achieved, usually it is said there is no optimal solution. For that one, what we are doing to make it optimal, first we are finding out that z j minus c j is less than 0 for how many variables. For this problem, you have seen it is for two variables x 1 and x 2 for the first two columns, which corresponds to a 1 and a 2. So, therefore, I am adding a new constant x 1 plus x 2 less than equals m. Then I am adding the slack variable and I am making this new less than equals type constant into equality constant. Now, I have to see, I have to replace one variable. How to replace the variable? To replace the variable, I have to find out which is the maximum of z 1 minus c 1 and z 2 minus c 2 in their modulus values, and I am finding maximum is 3. Maximum is 3 is occurring with respect to column x 1, that is the variable x 1 will be replaced in the original objective function and original constraints only, not on the new constant, and the value will be x 1 will be m minus this thing. Then by substituting the value of x 1 in the original problem, I am reformulating the problem like this. Again I have to create the initial basic feasible table. For that one, the basis in the basis I will have x 3, x 4 and x m as the basic vectors in my table. So, from here let us formulate the table. So, I will have x 3, x 4 and x 5. So, here it is a 3, a 4 and a 5. The values are a m I have written at first, a m corresponds to this x m, a m corresponds to this x m that I have written first. So, minus 3, 0 for x 2 it is minus 1, then for these two are not present. So, it is 0. Your C B values will be in that case x 3, a 3, a 4 and a 5 and 0, 0 and 0. These values will come as I am directly again I am writing minus 2, minus 1, 0 minus 2 minus 1, sorry, I am no, how minus 2 will come. This is 5 minus 2 m, 3 minus m and m. So, these values will be 5 minus 2 m, b values. So, b values were 5 minus 2 m, 3 minus m and m. So, 5 minus 2 m, 3 minus m and m. Here it will be minus 2, m is minus 2, then it is 0 minus 1 1 0 minus 1 0 0 0 1 and 1 1 1 0 0. So, if you calculate Zj minus Cj value now, you will find 3 0 1 0 0. So, your Zj minus Cj is greater than equals 0 for all j. So, once you have added the new constraint and after that you have added the slack variable, you see your Zj minus Cj has condition, optimality condition has been satisfied. But since m is very large, therefore, your these basic variables are not negative. So, which one will be the departing variable? I have to find out minimum of x bi where such that x bi less than 0, that is minimum of 5 minus 2 m and 3 minus m. So, minimum of these two will be obviously 5 minus 2 m, and 5 minus 2 m corresponds to which one? X 3. So, therefore, your x 3 will be the departing variable, x 3 will be the departing variable, which we have explained earlier, and x 3 will. So, x 3 will leave. Similarly, to check what will be the entering variable, you have to calculate maximize Zj minus Cj and y 1 j, because of the first one, this was the first row. So, y 1 j. So, this will be equals to maximum of what value? From this row I will take only those y's where the values are negative. So, I will take only this and this. So, the ratio Zj minus Cj. So, it is 3 by minus 2 and next one is 1 by minus 1, 1 by divided by minus 1. So, minimum is minus 1 and minus 1 is occurring for which variable? This is for x 2. Therefore, your x 2 will enter into basis, x 2 will enter into basis. So, your x 2 will enter, this will be the pivot element. Now, I hope it is clear to you that how to calculate what will be the entering variable and what will be the departing variable. So, from this table now x 3 will depart and x 2 will enter. So, the next table we can write it as x 2, x 4 and x 5. Here it will be a 2, a 4 and a 5. Cj values are minus 3, 0, minus 1, 0 and 0. Cb values will be a 2 is minus 1. So, 0, 0. So, I am just writing the values again, 2 m minus 5, it will be minus m plus 3, minus m plus 5. So, it is 2 0 1 minus 1 0 minus 1 0 0 0 1. You should check these values. I am directly writing because of the time constant, minus 1 1 0 1 0. If you calculate Zj minus Cj value, it will be 1 0 0 1 0. Again you see your Zj minus Cj is greater than equals 0 for all j, but all x b are not negative. At least here you have to check all x b are not greater than equals 0. So, feasibility condition is not satisfied. So, you have to first check what is which vector will depart. So, minimum of x bi where x bi is less than 0. So, minimum of This will be now positive 2 m minus 5 because m is very large. So, you have only 3 things 3 minus m and this is 5 minus m. So, minimum is 3 minus m and 3 minus m occurs for with respect to x 4. So, your x 4 will depart. Okay. So, the variable x 4 will depart, will leave, and now I have to calculate the which vector will enter. So, z j minus c j by y, this is second row. So, it will be y 2 j, where y 2 j should be less than 0. I will check it where y 2 j is less than 0. Y 2 j is less than 0 in this row at only one place. So, it is maximum of 1 by minus 1. So, it is minus 1. This corresponds to for A m. So, therefore, A m will enter into the basis in the next iteration and A 4 will go out. Fine. I think it is quite clear that A 4 will go out from this table now. So, in the next table what will happen? In the next table x 2 will be there, x 4 will be replaced by the x m and x 5 will come. So, that this will be A 2, A m and A 5. Your values are minus 3, 0, minus 1, 0 and 0. So, it is A 2 is minus 1, A m value is minus 3 and A 5 is 0. So, on this table your pivot element will be this one. In the earlier table your pivot element is this, means I have to make this element as 1 and the other elements as 0 on this particular column. So, after doing this I will find that 1 0 0 1 minus 1 2, this is m minus 3 1 0 0 0 minus 1, this one will be 2 0 1 0 1 minus 1. So, that now calculate the z j minus c j, you know it 3 minus 3 plus 3. So, it is 0, next one is 0, next one is 1, it is 0 1 minus 1 plus 1 0, here it is 1, this is 0, this is 0, this is 0. So, it is 1, here it is minus 1 into 2 minus 2 plus 3 1. So, this is 1. So, now you see your z j minus c j is greater than equals 0 for all j. For this problem z j minus c j is greater than equals 0. Your x b j greater than equals 0, x 2 value is 1, x m is m minus 3, where m is sufficiently large, therefore, x m also will be greater than equals 0 and x 5 is 0. So, x b 0 is greater than equals 0 for all j. So, your optimality condition as well as the feasibility condition both has been satisfied in this case. So, once this is satisfied means we got the optimum solution. So, now what you do? You delete the row corresponding to the this artificial variable, that is x m over here and over this. So, basically delete the row and column corresponding to the artificial constant, not constant. We added the artificial constant over here. If you see in this case, here we added the artificial constant like this way, and where x m was your slack variable, and x m, since x m is the slack variable, after that you have reformulated the problem by replacing one variable x 1 over here, and how we derived whether it will be x 1 or x 2, it depends on this thing, maximize of z 1 minus c 1 comma Z2 minus C2 in their absolute value, and from there I am finding maximum value is 3, which corresponds to the variable x1. So, we replaced x1 in the original objective function as well as original constants, but the new constant, the variable x1 was present. Then we formulated the new simplex table. Then we saw that xbj is less than 0 here. So, we are finding the depart variable and what will be the entering variable, and we are repeating the process. Now, at the last stage, what we are finding for both zj, for the last table, both zj minus cj greater than equals 0 for all j, and all xb's or xbj greater than equals 0, which is evident from here. So, in the next table, what you do? You remove the row and column corresponding to the artificial constraint, that is, for xm row you remove and am row also you remove, and rewrite the entire table once again. So, that now you will have this xm will not be there, you will have only x2 and x5. I am using. So, this is your x5 over here, the original problem x3, x4, x1, I am sorry, x not, this will be x1, this will be a1, because otherwise this will not form the basis. This is x3, this is x4, this is x1. So, this is a1. Here also this will be x1 and a1. For this case also this will be, just make the changes, this will be a1. So, this is x1 and this. So, here you will have x2 and x1. So, that you have a2 and a1. So, 0 minus 1 0 0. So, a2 is minus 1, it is 0. So, you are just writing from here by removing the xm row and the column corresponding to am. So, b values will be 1 2 0 1 minus 1 2, and this is 1 0 1 minus 1, zj minus cj is 0 0 1 2. As we have told already that the optimality condition zj minus cj greater than equals 0 is satisfied. Feasibility condition xb, that is x1 and x2 greater than equals 0, that is satisfied. Therefore, your optimal solution is x1 equals, optimal solution is x1 equals 2, x2 equals 1, and z max value will be equals to, there will be, what was the original problem? Your original problem, it is zj minus cj. So, 3x1 plus 2x2 was there. So, therefore, this will be minus 1 and minus 3. So, z max will be 8. So, the optimal solution is x1 equals to x1 2, x2 1, and the maximization problem, it was z equals 3x1 plus 2x2, and from here I can obtain the value as 8. So, by this way, even if when zj minus cj is not greater than equals 0, what we have shown here, I can make it greater than equals 0 by adding a new constraint and then use the slack variables and use the dual simplex procedure. So, I hope it is clear to you that how to solve the dual simplex problem for various other types.